What's going on YouTube? Welcome back to another Tutortopia video. So in today's video, we're going to be going over some more of the higher order inhomogeneous linear ordinary differential equations, as we can see in the name right here. So the first part is we're going to have a linear ordinary differential equation. So that's just basically what we have right here. As we can see, the n and the n minus 1 denote how many derivatives we're taking, and then the cn minus 1, all the way up to the C1 and C0 are all just constants. And then we have an inhomogeneous part over on this side. So that is what we're going to be covering today. And specifically, I have two types of f of x's that come up pretty common. So we have number one is it doesn't really matter, but let's just say some constant times e to the a times x. And then the second one, so this is basically an exponential. And the second kind of forcing term, so this inhomogeneous part is also called a forcing term, can be a polynomial. So let's just say c2 x squared plus 5, I don't know. So some polynomial. Okay, so let's do a quick example of a second order linear differential equation. Let's just call it a y double prime plus by prime plus cy is equal to, and then let's just do e to the ax. Shouldn't use a again. E to the c1x. Okay, so how would we solve this equation? Well, from our last video, we remember that we need to break it up into a y homogeneous equals dot dot dot, and then a y particular solution equals dot dot dot. So to solve the y homogeneous solution, all we need to do is come up with our characteristic equation, which is going to be a lambda squared plus b lambda plus c is equal to 0. Then we can easily solve for lambda right here by using the quadratic equation. So negative b plus or minus square root b squared minus 4ac all over 2 times a equals lambda plus and minus. I'll write it lambda plus and lambda minus. Okay, so that gives us the solution yh of x is equal to some constant, I'll call it c1, e to the lambda plus times x plus c2 e to the lambda minus times x. I'll get rid of the dot and make that look more like a minus. So we have our homogeneous equation, our solution, and that's pretty easy. So now how do we get our particular solution? So that's kind of the question. Okay, so for an exponential, we kind of know in advance that the derivatives of exponentials are also exponentials. So we know, so we kind of guess that we have a solution y particular of x is equal to, let's use d1 e to the c1x. Okay, so I know that this can kind of look like it's coming out of nowhere, but I just want to kind of explain kind of the thought process of how we could come up with this ourselves. So right here, we use C1, and we use C1 because it's actually the same constant as up here. So it makes sense that when we take the first derivative and the second derivative, our exponential is still going to be like e to the same whatever, right? E to the same c1 of x, and then you're just going to be bringing down that c1 when you take the derivative of exponential. So in order to solve this particular solution, the answer is probably going to have the exact same exponential constant in it. So that's where we get the c1 term. And then since we don't know exactly how this derivative should be, or not derivative, what this constant should be, we can just figure it out later. So we just leave it as d1. Okay, so now we can plug this into our governing equation, which is right here. And we get that a times c1 squared times d1 e c1x. So this is just taking the derivatives of this. So I'll write it out here first, I guess. d1 c1 e c1x y prime, or y particular double prime, is d1 c1 squared e c1x. Okay, so then that's where we got that term right there. And then we have plus b times y particular prime. So that's going to be d1 c1 e c1x plus c d1 e to the c1x must equal e to the c1 of x. Okay, so what's really cool is that we can see that all of these cancel out. So we can always just divide through by the e. And then that becomes a c1 squared d1 plus b d1 c1 plus c d1 must equal 1. So now, what is the constant that we're trying to solve for? Well, our underdetermined coefficient, or undetermined coefficient, is right here in our y particular guess. So we're trying to solve for d1. So in this equation, in order to solve for d1, we're going to say that d1 is there, there, and there, so we can just pull it out. So d1 equals, I guess we could do the algebra, a c1 squared plus b c1 plus c equals 1, which then goes to d1 is just equal to 1 over a c1 squared plus b c1 plus c. Sweet. So we found our particular solution. So our particular solution uses both of these, and we get e c1 of x all over a c1 squared plus b c1 plus c equals y particular of x. So now we're pretty much done. All we need to do is combine our homogeneous solution with our particular solution, and we get the full solution. So I like to say our total solution, which is the subscript t right there, is equal to, so this will be c1 e lambda plus times x plus c2 e lambda minus x plus, so I'll write it out again. So this is my y homogeneous of x plus e c1 x all over a c1 squared plus b c1 plus c. And then I actually did a little bit bad notation because this c1 actually isn't the same as this c1, because this is an arbitrary constant right here, and this one is actually given in the problem right there. So let's change our initial condition constants to be, I don't know, d's. That'll be easy to fix. So be d1, d2, d1, d2. There we go. And then if we're given initial conditions, so y of 0 equals 0 and y prime of 0 equals 0 or something like that, we could easily plug these in and then solve for our d1 and our d2. Cool. So now the second type of equation that I would like to go over is going to be the polynomials. Cool. So again, let's just say that for our equation, we already know how to get y homogeneous equals, let's just call it, it's the same as last time, d1 e lambda 1 times x plus d2 e lambda 2 times x. So this is just using any of the methods that we have gone over before. It doesn't really matter what lambda 1 and lambda 2 are. They're just something. So this probably comes from a second order ODE equals, and then let's go with a polynomial. So now the question is, how do we solve for the particular when we have a polynomial? So let's use the same situation, a y double prime, by prime, cy equals some polynomial. So let's start out with an easy polynomial initially. So let's just start out with 1, right? 1 is just a degree 0 polynomial. So what's the particular solution to this? Well, we know that this could equal some constant, right? A constant times some y particular would also equal a constant. So that would be good. And then when we took the derivative of a constant, it would equal 0. And when we take the derivative of 0, it'd be 0. So that one would be 0 and that one would be 0. So for a order 0 polynomial, which is just a constant, we know that our y particular of x is just going to be some other constant. Let's call it temporarily d1. Not to be confused with this d1. I'm just kind of running out of arbitrary names. So let's call it d1. And then we can plug it in. So we get c times d1 equals 1. And then the derivatives just vanish. They go to 0. So then we get d1 is equal to 1 over c. And we're happy because that was nice and easy. Okay, but now let's have this be a little bit different. So let's have it be the next polynomial. So let's have it be x. Okay, so what would this go to? Well, I know that if this is an x, then the derivative of an x would be some constant, and the second derivative would be nothing. Okay, so in order to have nothing, I know that the highest order polynomial that I can have is going to be the same order as like this one right here, right? Because every time I take the derivative of a polynomial, I'm going to be going like down, right? Because like x squared will go to x, 2x. So we can see that the order of the polynomial decreases from 2 to 1. So that means that the y term is going to give us the highest order polynomial that we can have. Okay? So we guess that our y particular is just the most general polynomial of order 1, which would be d1 times x plus d2. Okay? So we plug this in. So that means that y prime would equal d1, y double prime is equal to 0. Okay? So then using all three of these, we get a times 0, right, plus b times d1 plus c times d1 of x plus d2. And that must equal x in this case, right? Okay, so how do we solve for our two unknowns, which is d1 and d2? Well, it's the exact same as when we did partial fractions back in Calculus 2. So we get all the x terms together, and we get all the non-x terms together. So this is going to be c d1 of x plus, and then I'll group it real quick, plus b d1 plus c d2 is equal to x plus 0. Okay, so we can match our coefficients. So this coefficient is 1, match that with this coefficient, and then this coefficient is 0, so match it together. Okay, so doing that, we get c d1 is equal to 1, and then we also get b d1 plus c d2 is equal to 0. Okay, so this is the easiest one to solve for. So we get d1 is equal to 1 over c, which then we can plug back into right there, and we get b over c plus c d2 is equal to 0. So we could subtract it and divide it again. So we get d2 is equal to minus b over c squared. Sweet. So then we get our y particular is equal to d1, d2 are right there. So we can plug that back into our initial guess, and we get x over c plus minus b over c squared. Cool. So we're happy. So in general, if we have a equation that looks like a polynomial of order n on this side, our guess solution, so our y particular of x or t, whatever, it doesn't really matter what that variable is, because you can call it whatever you want, is going to be a general polynomial of order n. Okay, so it's going to be p, let's see, I'll call it dn xn plus dn minus 1 x n minus 1 plus dot all the way down to d2 x squared d1x plus d0. So that's going to be our solution, or our guess for our y particular, and then we're going to have to solve for each and every one of these unknown coefficients, which can kind of be a pain because, as we can see, in this case we're going to have n separate equations, and that's just probably going to get very messy. So usually the most that you'll see in like exams is like a squared, a polynomial of order 2, and even that can be a little bit much. Okay, so last thing I want to go over in this video, just really quick, is what happens when we have combinations of forcing functions. So let's say that we have e to the c1x times some polynomial of order n. Okay, so for these, what we actually have to do is we just combine our y particulars, our y particular guesses, I should say. So we just have it go c x times dn xn dn minus 1 x n minus 1 d2 x squared d1 x1 d naught. So as we can see here, just like how we just multiply these two together, we just multiply our two guesses together for our y particulars. So if your course is rude enough to give you a problem like that, this is all you have to do. And then, yeah, so this is pretty much all I wanted to go over in this video. And in the next video, I'll probably start to be going over some linear algebra so we can get into coupled differential equations after that, and then start doing some end of the year stuff. All right. Thank you so much for watching. If you liked, make sure to subscribe, like the video, spread it to your friends that are taking linear algebra, and I will see you next time.